Hi, and welcome to the third in our Railvolutionary webinar series. My name is Tobias Liljedahl, and I will be your host today. And with us we have Jan Babka. Welcome, Jan. Can you briefly tell us a bit about yourself and what you're going to speak about today?
Hello, Tobias. Hello, everybody. Before I even start to introduce myself, let me ask one question. If you are a bogie designer, how do you decide which type of wheel bearing to use? I don't mean what size of bearing, but really what kind. If you go rather for taper roller bearing unit or cylindrical roller bearing unit, or maybe some other bearing type, maybe you have a good technical answer to this question, but maybe not. Maybe you are just using the bearing type historically used by your company or in your country. And that question, which bearing type is the most suitable one, is the subject of today's webinar. Whether the right type of wheelset bearing can be selected based on technical arguments, or whether tradition should be followed. And I believe at the end of this webinar, you will be convinced that your choice of wheel bearing for a given application should not really be a decision driven by tradition, but it should be rather your logical choice, because you will receive the technical arguments you need today. But now let me finally introduce myself. My name is Jan Babka, and I am a manager of SKF Global Railway Application Competence Center. In this engineering team, of course, we deal very deeply with railway wheelset bearings practically daily. So I want today to analyze the question of optimal bearing type really from engineering point of view. It means looking on the physical model of the railway vehicle and the role of rolling bearing in it. But let's first look back into the history. The railway wheel bearing has developed over the time from oil lubricated plain bearing over ball bearings, spherical roll bearings, cylindrical and taper roller bearings, up to today, up to now, to bearing units. During this evolution, and also depending on where in the world people used and developed trains, different designs of railway wheelset bearings have appeared, and guess what? Some of these types are still in use. It is quite surprising to me, and I wonder why. Why don't we have one unified, optimal engineering solution? It should be like this, because the general principle of a railway bogie is the same. We have rotating axles, and we have railway vehicle body sitting on them. And what we need is to ensure the transmission of force and rotation with minimum losses. We need maximum reliability, easy assembly and disassembly, and minimum maintenance costs. So the technical specification of our problem seems to be simple. So one could believe that there should be one optimal engineering solution for railway wheelset bearing. One type of wheelset bearing used in all railway vehicles around the world. Why do we still use different types? Let's have a look on advantages and disadvantages of these different types of wheelset bearings we can see around the world today. Let's start with the classic one, the spherical roller bearing. It is one of so-called open bearings, which are used in a railway axle box, usually in pairs. Another example of such open bearings used in pairs could be two single cylindrical roller bearings. But let's talk now about spherical roller bearings. The spherical roller bearing has one great advantage, and that is that if we load it with a radial force from the top, this radial force is distributed perfectly evenly on all four rows. We have two bearings, altogether 4 rows. All of them are equally loaded by this radial load. This is due to the fact that the outer rings of spherical roller bearings are axially free. There is no spacer between them. There is a gap. So the outer rings can automatically find their optimal position when we load them. However, at the same time, this advantage of axially free outer rings represents also a major disadvantage of spherical roller bearings, because their free axially movable outer rings in the housings generate so-called fretting corrosion between the rings and the housing bore. And the fretting particles can fall freely into the interior of the bearing and contaminate the grease there. This is really not good, and the fretting may cause big troubles, especially in case of faster applications. But it was seen, for example, also in metros. But now let's go to another type of wheel bearings, the TBU taper bearing unit. Here I have one. This bearing type has actually several advantages. Let me start with one of the most important. A huge advantage, which is obvious mainly when the train passes a curve, concerns the axial force. The axial force is generated by the centrifugal force of the railway vehicle going in the curve. So this axial force is in the TBU mainly transferred by the inclined tapered raceways, where the energetically favorable rolling friction occurs. Only about 20% of this axial force is transmitted through the faces of the rollers and the inner ring flanges. It means in the area of unfavorable sliding friction. So this is the big advantage of the taper roller bearing units. It manages very well the curves. On the other hand, it is necessary to mention that the inclined raceways of a taper roller bearing units cause at the same time something which is less favorable. And it is that even when the train is running on the completely straight track and the bearing is loaded only radially, this radial force is always partially transformed into the certain axial force, which even on the straight track acts against the inner ring flanges. This phenomena of generating of axial force on the flanges, even on straight track, does not exist in the cylindrical roller bearing units because their raceways is not conical. This we can see on the upper picture. It shows the situation when the train is going absolutely straight, so that the CRU, cylindrical roller bearing unit, is loaded purely radially from the top. In such situation, the rollers transfer the radial load into two radial reactions acting on the inner rings, and there is no axial load acting on the flanges at all. This is, of course, very comfortable situation for the CRU, because in such situation, there is no sliding between no sliding friction between the roller faces and the ring flanges. It is not fully true because also on absolutely straight track, the train moves from right to left in periodical sinusoidal movement, but I do not want to be too complex. Another advantage of CRU is that due to the cylindrical shape of the rollers, the CRU roller set does not transport the grease from the bearing center toward the seal, as it is happening in case of taper roller bearings. But let's have a look on the picture in the lower part of this slide. It shows CRU in the situation when the train goes into the curve and the vehicle centrifugal force generates axial load in the bearing. And this complete axial force must be in CRU transferred by sliding friction contact between the roller faces and the ring flanges. And this is, of course, a big challenge for this bearing. The sliding friction under load is the most sensitive area of a CRU. So now, after disclosing several advantages and disadvantages of different types of wheelset bearings, it is probably clearer that it is not so simple to declare who is the winner. Which bearing type represents the optimal engineering solution for our railway bogie? You have seen three railway wheelset bearing types. Each of them has advantages, but also disadvantages. So the engineering choice for just one of them is just not that easy. These two, the TBU and CRU, are the ones predominantly used today because they are not just bearings, they are bearing units. It means they consist of bearings, sealing system. They are already pre-greased and pre-assembled from the bearing supplier. This makes them a quite comfortable solution for the user. It's practically a black box for the fitter. One can say it's a plug-and-play solution. So a bogie designer will most probably face to the decision, should I take a TBU or should I go rather for CRU? And interesting enough, something that I and my team see quite often, this question is getting answered not based on the proper evaluation of the technical advantages of these two bearing types, but simply based on tradition in the given country or a given company. And therefore, we can find the taper roller bearing units, TBUs, mainly in United States and countries which in the history were influenced by American railway technology. This was mainly valid for the freight applications, what I have said right now. But with the time, the TBUs spread very quickly also to passenger applications, almost all over the world. On the other hand, the cylindrical roller bearings, because cylindrical roller bearing was invented in Germany, greatly influenced other European countries and is therefore still commonly used all over the Europe in form of pair of single open cylindrical bearings or in form of bearing units CRU. But not only in Europe. We will find them also, for example, in the fastest trains in the world, in China. And finally, some countries still use spherical roller bearings, mainly for freight applications and mainly due to tradition. But back to our engineering considerations. Okay, so we need the bearing unit. That's for sure. It's clear. We have mentioned several advantages of the bearing units. Either TBU or CRU, because a unit has many advantages against the open bearings. However, we have not yet answered the question, which of the main two types, TBU and CRU, is better from an engineering point of view? And let me tell you, this question cannot be answered just like that, simply for the fact that the question is not correctly phrased. Fact is, for some types of applications, or rather, some types of lines, routes, the TBU is better, and for others, the CRU is better. For curvy routes, it is better to go for TBU. For less curvy lines, for rather straight lines, is the CRU a better choice? I think you can see it well here on this slide. You can see schematically how much or how little energy intensive contact is between the roller and the bearing rings in the TBU and in the CRU. We have learned that the contact between the roller and ring happens in two areas. On the raceways, where it happens by means of rolling friction, which is more beneficial in terms of energy losses, and on the roller faces, where it happens by means of sliding friction, which is less beneficial in terms of energy losses. Looking on energy losses in these two areas, raceways and roller faces, we can conclude that for straight lines, the CRU is more suitable. And for curves, the TBU is more suitable. But there is one big but, because among TBUs, there are different versions producing different high energy losses. And also among CRUs are different versions generating different high energy losses. So the best results in terms of energy loss minimization are achieved by TBUs and CRUs versions, which are intentionally designed to generate low friction, low energy losses. These versions not only reduce the overall energy consumption of the railway vehicle, but at the same time, it is possible to extend their maintenance interval as they run cooler, which is good for the grease life. And this is just another of showing what you have seen on the previous slides. The higher ability of TBU to manage curves and higher ability of CRU to manage the straight lines. This chart shows the dependence of the forces acting on the ring flanges on the total axial force acting on the bearing. It can be clearly seen that on straighter tracks, the CRU suffers from far less sliding friction than the TBU. However, when we have curvy lines, the TBU is an advantage here. In reality, both TBU and CRU will work well enough in most applications. But wait a minute, it's not just about the functioning or not. The industry is entering an era where functioning is not enough anymore. Each component is being investigated in detail for how much it contributes to the vehicle energy losses and to the carbon footprint. That's why it is becoming more and more relevant that for each individual application and track, the suitability of using either TBU or CRU is analyzed in terms of energy losses. More and more, the determination of energy losses will be the criterion that will decide for a given specific application whether a CRU or a TBU should be used. But as already mentioned, even between the individual variants, there are differences in terms of the amount of energy losses. So in the end, both TBU and CRU are the winners, but in their low friction versions. But I do not want to go into details about low friction in this presentation today and keep this for another time. So now it's time to go to Q&A. Let's switch to Tobias in the studio.
Thank you, Jan. Really interesting topic. Let's see now what questions our audience has for you. We will try to answer all of the questions, and in order to do so, we have our colleague Doris in the chat managing the Q&A. But Jan, let's start with the first question here. Do individual bearing types show different typical damages?
Okay. I have been talking in my presentation about bearing units and open bearings. So this question could be answered like this. Because the bearing units are pre-assembled, sealed, and pre-lubricated from the bearing supplier's factory, where all this done in clean, controlled environment of the bearing supplier factory. So therefore, bearing units are, for example, much less sensitive to contamination during handling or assembly, and therefore they are also relatively less sensitive to failure mode, which is called surface-initiated fatigue. Okay, the surface-initiated fatigue is more likely to be observed in open bearings. However, since the bearing units are usually applied with much longer maintenance interval compared to the open bearings, we can find the mentioned surface-initiated fatigue in bearing units as well. But with one big difference, this failure mode, if it occurs in a bearing unit at all, it occurs much later. And it's rather caused by degradation of lubricant, not by contamination. So this is how I would answer this question.
Thank you. Let's move on to the next question. What about electric current passage? Is it right that some types of bearings resist electric current more than others?
Okay, the passage of electric current cannot be solved by choosing a different type of bearing, because the electrons, they flow in the same way through a spherical roller bearing, cylindrical roller bearing, or tapered roller bearing, and they create the craters on the bearing raceways, which is the damage. But there is one exception, and it is that the units, taper bearing unit or cylindrical roller bearing unit, can be, and they not only can, they are also being supplied in the INSO-code version, which means with a ceramic insulation layer on the surface of the outer ring or in the bore, that reduces the risk of electrical current passing through the bearing.
Thank you. Are there any differences concerning bearing mounting and dismounting when looking at the different bearing types?
I have again to come to the difference between open bearing and the units. The fundamental difference can be seen between these two groups like this. The bearing units, PBUs or CRUs, are assembled by relatively quick and simple cold mounting using hydraulic press. The same for their disassembly. Again, it is in cold way using a hydraulic press. While the open bearings, such as a spherical roller bearing or cylindrical roller bearing, are assembled by heating the bearing to a temperature over 100 degrees Celsius and then sliding down by mounting sliding on the cold journal. Of course, this operation, heating up and so on, this is a disproportionately more complicated operation, and it takes also longer time.
Thank you for that explanation. Here's someone that picked up on what you told earlier. Interesting, you mentioned a low friction version of axle bearings. Does this mean the market already use or want them?
Yes, this is right. Customers are already demanding low friction axle bearings variants, and this for two main reasons. First, the low friction bearing contributes to the reduction of the total energy loss of the railway vehicle. This contribution may seem relatively small compared to other components of the railway vehicle. However, we must not forget that a railway vehicle is in the vast majority of cases has 8 axle bearings. So this contribution adds up. And the second good reason why customers demand low friction bearings is that such a bearing works at a lower temperature, which automatically means a significant extension of the grease life.
Thank you very much. Next question. Are there differences between individual types of bearings when it comes to refurbishment? Which one is better?
Okay, from technical point of view, it is possible to perform refurbishment on any type of railway wheelset bearing or bearing unit. Of course, the individual technical steps in the refurbishment process will differ for different bearing types. For example, during refurbishment of taper bearing unit PBU, it is necessary to readjust the axial clearance by inserting a central spacer with the appropriate width. This operation is completely omitted when we refurbish a CRU because no axial clearance is set in a CRU. So this is from technical point of view. However, from an economic point of view, it is more advantageous to perform refurbishment on bearing units due to their complexity and the safety critical nature of their application. For the units, we need, or the workers need special skills, tooling, and also precise documentation. These processes are delicate and special care must be taken during refurbishment to ensure that the bearings are restored to their original as new condition. Therefore, it is safer and more economical to have refurbishment of such units performed by qualified and certified refurbishment centers in order to get the most out of the wheelset bearing unit.
Thank you, Jan. I think that answers it. What is the realistic friction power loss reduction in an application?
This is difficult to answer, to be honest, because we do not have one representative friction value of a bearing or bearing unit. We need to look on individual spectrum, speed and load spectrum, and then we can answer this question. So it's difficult to give one answer, but it will be in order of a tenth of percent.
Okay.
Not 10%, order of tenths.
Okay, yeah. And if you need more explanation, you're most welcome to contact your local SKF
Definitely.
representative or railways at skf.com as well if you need even more. But we'll crack on with the next question here. Do you think it's possible to come up with some new type of railway axle bearing since the design of the ones you mentioned are quite old?
Okay, it is true. These principles, rolling principles, are very old. In other areas of industry, we have seen relatively recently some revolutionary discoveries in world of rolling bearings. Like, for example, a completely new type of rolling bearing, which is called carb. Carb is bearing type which is combining the self-aligning properties of the spherical roller bearing with the ability to accommodate axial displacement like a cylindrical roller bearing. Carb cannot be used in railway axle box as it does not support axial loads. Therefore, it is used in other applications, like, for example, in wind turbines or paper machines. But back to your question. I personally do not see any great possibility that some completely new rolling principle will enter the field of railway axle bearings. That some completely new type of railway axle bearing will appear. But this is my opinion. Of course, it's possible that I am wrong and some clever inventor will surprise us and will come up with some revolutionary new principle.
Yeah, let's see what the future shows. We'll go on here. Here's someone that says, agree, units have a number of technical advantages, but they are much more expensive than open bearings. Do you really think that bearing units can be successful in freight? As a bogie designer, I must choose components that won't make the bogie unnecessarily expensive.
Yeah. It's logical that the purchase price of a bearing unit is higher than the purchase price of an open bearing, simply because the bearing unit contains more components, it contains more added value. However, it would be a big mistake to judge the financial efficiency of a bogie only based on the purchase price of its components. The overall picture of the financial efficiency of a bogie is formed by its purchase price or purchase price of its components, but also by bogie maintenance costs during the whole lifetime and costs spent to solve unexpected technical failures. And in both, especially in both these two last areas, maintenance costs and the costs of unexpected failures, bearing units win clearly over open bearing. Why? This is because the bearing unit is for a bearing unit it's possible to much more extend the maintenance interval. In the optimal case, to harmonize the bearing unit maintenance interval with the replacement interval of the wheel. This is not possible with an open bearing. Or it is possible, but at cost of the risk of a high field failure rate. plus the bearing units, because they are closed, pre-greased, sealed units, are far less sensitive to unexpected field failures, as we have discussed already before.
Thank you, Jan, and we're very happy about all your questions, but unfortunately now time is up. So you'll receive also access to this recorded webinar in the next couple of days. And in the meantime, you're most welcome to contact your local SKF representative if you have any additional questions, or email us at railways@skf.com. And we would like to thank you all for joining today, me and Jan. And we hope to see you again on our next Railvolutionary webinar Wednesday. Goodbye.
Thank you very much also from my side for your attention.
Thank you. Goodbye.